Lab Guy here. Long time no E, no C. Sorry about that. I have no excuses. There always seems to be more important necessities of life over making videos for you nice folks. Before we go any further, I would like to immediately thank and welcome all of the new subscribers to my channel. I'm sorry I've been slack on getting a video out for you. I have no shortage of ideas of things to cover, but I want to make short videos, and none of the subjects lend themselves to making short videos. I've been working on a couple of various projects, mechanical TV related stuff, of which I'm making very little progress. Some of the people I've collaborated with either don't know the answers or they don't understand my questions, and so I'm kind of stuck between the rock and the hard place in that endeavor. I've been working on some amateur television equipment for analog ham radio television, and that has hit a snag. I'm pretty certain that I know what it is, and that will entail literally taking the whole transmitter apart and rebuilding it a second time. But the individual components appear to work in that project. Look forward to a video about that eventually. Hopefully I'll live long enough to complete it. In recent news, my friend Troy Walters at Troy's Visual Arts channel on YouTube has resurrected his Iconoscope TV camera project and has been working on it. I've been helping where I can. He has several overlapping issues with the original design, camera design, that he chose to construct the project on, along with there's some design issues built in. There's some modifications that I talked him through. We didn't realize until just recently they were not working. Some of the issues are with Troy and his full understanding of the interrelationships of the various circuits, which is not, I'm not saying that's a bad thing at all. Anybody who gets into really doing a deep dive into an analog television camera will hit these conceptual confusions. It takes time to put the pieces together. So today I'm going to walk through the most recent issue we found and talk about some of the circuits. It revolves around how people of various experience see a schematic diagram when they look at it. For instance, if you had a schematic of a black and white analog television and you folded it out on the table in front of you and you looked at it, and you have electronics experience but no experience with something that complicated, you'd glance at the schematic and what you would see is a television. The whole thing would be a television. And then as time goes on and you build things, you start to recognize functional blocks, and pretty soon you look at that same schematic and you go, oh, there's a television, there's a radio receiver. Or it's the television receiver, it's a radio. Then, oh, there's a high voltage power supply over here. Oh, there's a deflection circuit. Here's an audio amplifier. Instead of seeing a television, now you're starting to see individual blocks. Now you may look at those blocks, and when you look at the audio section, you go, oh, there's an audio amplifier. But it's made of like 3 tubes, let's say. And then eventually you'd look at it and you go, oh, there's a detector and a preamp and a power amp. And so on. And as you go on, you see the finer and finer detail. It's kind of fractal in that way. It's self-replicating as you descend into the layers. It's like Shrek said, it's like an onion. It has layers. And some of them are smelly, especially if you put too much current through them. So ham radio. So I'll stop putting you through this torture and go to the next scene where I will discuss the transistor circuit that we fixed for Troy and explain how and why it works. We'll be looking at 2 transistors and an LM555 timer, or in Troy's case an NE555 timer. It's the same part. And we'll take it from there. This is a schematic of Troy Walters' television cameras horizontal scan master clock circuit. The NE555 timer is set up as a free running oscillator. I'm not showing the timing components here, but it's set to run at about 15.634 kilohertz, which is the horizontal frequency, and it outputs a low going pulse in time with that, which drives the horizontal scan transistor, and some one-shots which create pulses that are added to the video downstream. For most of its life, Troy ran this camera in free running mode, or internal mode, which is with the reset pin of the 555 pulled up through a selector switch. It's pulled up to 15 volts. The oscillator is running on 15 volts. The fellow who designed the camera used CMOS logic family parts that could run on up to 20 volts, I believe, or 22 volts, so that he didn't need an extra power supply for logic. I use 5-volt logic. I've always used 5-volt logic, and I will always use 5-volt logic. So I built a sync generator for Troy and sent it to him, and he integrated it into his camera, which already contained circuitry to allow selecting external sync and buffering an incoming low-going horizontal drive pulse. Horizontal drive is the name of the signal from a sync generator that drives the scanning circuits in a camera. It's specifically made for driving horizontal scan only. So, it's being received into this 2-transistor circuit, which is 2 logic inverters, because the polarity of the reset pulse for the 555 is the same as the incoming signal. The difference is that the incoming signal has a range of 0 volts to plus 5 volts, and the reset pin is wired on the 555 for an operating range of 0 to 15 volts, so the 2 transistors form what we call a level shifter. And because a transistor inverts a pulse and flips it over, this will not work for the reset, so he flipped it once and then flipped it again so that he had the correct polarity to reset the 555. Well, for people in the know looking at this circuit, you can see plainly that there was an error on the original schematic. This circuit doesn't work. And this is what Troy recently discovered as he was experimenting, and he was getting an anomaly where the top of his video picture was tearing, where it would go into vertical sync, and when it came out of vertical sync, the lines were shifted one way or the other because the sync pulse was not getting through this and reaching the 555, which was free running. All right, and not only that, yeah, it was free running. Luckily, this pin was high. This transistor never switched. And what's wrong here is there's nothing to pull this collector up. I don't know if the original designer did this on purpose, because a correct sync generator, a real sync generator, puts out a pulse that goes from 0 to -4 volts. Now this circuit might work with that drive. I don't know. It will not work with 0 to plus 5 volts, and the fix was very simple. We put the missing resistor in right here. That's a resistor, all right. And it's another 1K just like this one, so that we have essentially 2 identical circuits here. This one, the first one, does 2 things. it takes the 5-volt pulse, inverts it, and raises it to 15 volts. Okay, it's been inverted and level shifted now. This drives this base of this transistor off and on. And actually, it doesn't go to 15 volts. It's going to go to the 0.6 of a volt drop of this junction right here. But this provides the pull-up to turn this transistor on finally. And this point will go low. So this goes low, this goes high, this goes low. And comes through and resets the 555. And that was why Troy's camera was not in sync in horizontal. The vertical sync was working fine. That's the good news. So that is the story of Troy's horizontal sync problem. Now, the rest of the camera has other issues, and I will probably do a short video about each of those issues separately so that I don't pile a whole bunch of problems in one video. So this is my explanation of what was wrong in the initial schematic that Troy worked from. It was that this resistor here was missing. Thanks for watching. Stay tuned for more videos coming soon. And Lab Guy out.